some of the mass of the heavier nuclear form is less than the sum of the mass of small nuclei. Okay. So where the small mass has gone, that is called the mass defect, and the mass defect is being, if you know that the hydrogen is being forming, helium is being forming through the hydrogen in the stability binding energy curve. You have seen it was somewhat like this. It was somewhat like this. Helium is coming out to be over here. Have you seen that in the binding energy curve? Okay, from
Yes, sir.
hydrogen to helium. What is happening? Binding energy is increasing. Whenever the binding energy is increasing, this means some of the mass is being converting into energy. Okay, have you got that? So what the reaction is taking place in this fusion reaction for hydrogen? Here it is deuterium, one of the isotope of hydrogen. They combine together, and what they form? There are the two protons. They are combined to the how it will happen. This will happen when we heat a gas, hydrogen atom. When we heat hydrogen gas up to the temperature of, or I just ask you how this happen. First of all, how this reaction happens. It will happen at a very high temperature. Where at that high temperature, what will happen? When you heat a gas, so this is the nucleus of the gas. Electrons are revolving around the atoms of the gas. So when you heat the gas at a very high temperature, these electrons start eliminating the nucleus or atom, or this they overcome the attractive force by the nucleus. So after some time, what will happen? Only the nuclear part remains. Electrons are revolving, or electrons are being eliminated from the atom. What will happen if we further heat it up? So they are so excited, these nucleus of another atom being so excited that they have a kinetic energy of vibration, that they get close to each other at a range of 1 Fermi meter. Okay, 1 or 2 Fermi meter. They get close by getting the kinetic energy at that much high temperature, where they get close at a distance of 1 Fermi meter. At that distance, what will happen? The nuclear force start acting. Okay, force start acting. As the nuclear force start acting, it will start closing the proton together. Okay, and what it will form? Another nuclei which is having a two proton. Okay, have you got that? And in this process, in between this, doing all this, so many other steps of the process has been taking place that we will see there. Okay, but what is the initial condition? That we have to heat a gas at a very high temperature. Now we will see that at what temperature do we need to heat up it. Okay, so what is the kinetic energy of the molecule of a gas if we see through the Boltzmann, in terms of the Boltzmann constant? What is the kinetic energy? Can anyone tell? Anyone can give the answer? Uh-huh. Monoatomic gas. What is the kinetic energy for the monoatomic gas? 3 by 2 kT na? Bu is what? 3 by 2 kT. 3 by 2 K. That is the Boltzmann constant. kT it is. Kinetic energy. Okay. And if we see how much the kinetic energy we required, that is around 400 mega electron volt. For calculating this, the temperature is being required around, it will comes around 3 into 10 to the power 9 Kelvin. That much temperature is required for making the two protons close enough together at a range of 1 Fermi meter, where the nuclear force start acting on it. 3 into 10 to the power 9 Kelvin temperature is required. So this much of temperature is not possible to gain on Earth. Is it possible? Is it possible to gain this much of temperature on Earth? In laboratory we have achieved, but not exactly. And you have listened the news regarding this in 2 years before or 3 years before. In China, there is some artificial sun has been made. So let's listen the news. So for that, this is being required. So this means this much of temperature has been maintained there in the lab. Okay, in China. Not exactly this much, but 3 into 10 power 7 Kelvin, which is basically the temperature of the core of the sun, where the two nuclei of the hydrogen atom fuse together and form a helium there. Okay. Okay, Dave. How this we are getting this much of energy, 400 mega electron volt. You see, if there is a potential energy between the two charged particles, what that potential energy will be when their two protons are at separation of 1 Fermi, then what will be the potential energy? That is being E square upon K R, where R is being the 1 Fermi distance. Okay, this much is the energy which is being required. And if we calculate this much of energy at 1 Fermi, then this energy comes out to be 400 mega electron volt. And at this energy, the temperature is being required is being 3 to 10 power 9 Kelvin. Have you got that? So this much of temperature is being required for the fusion of the two nuclei of the hydrogen and forming the helium. So because of this, we are not able to harness this energy in we are not able to harness this energy for the commercial purpose. We have only harnessed this energy for destructive purpose. You have listened that the North Korea recently has tested his hydrogen bomb. Okay, have you listened that? There is a mountain there. When tested when they tested hydrogen bomb there, the mountain height decreased by some inches. Okay, they tested in deep earth, but when they tested this hydrogen bomb, then the mountain is there whose which height has been decreased by some inches. Okay, so that's why this nuclear fusion reaction is not being commercially used. Generally, our nuclear reactors are based on nuclear fission reactions, not nuclear fusion reactions. Okay, because it requires a lot of temperature and the energy is being harnessed is more as compared to the nuclear fission reaction, but uncontrolled energy is there. Okay, we are not able to control that energy because as this much of temperature is being reached, then further reactions take place by its own. Okay, now what will be the reaction that will take place? So first, hydrogen nucleus combine and form another isotope of hydrogen in which there are two protons. One is here, one is here. When they combine together, then they form one proton and one neutron. There is a one proton and one neutron. When the proton get converted into neutron, what that reaction is called? What that radioactive reaction is there? Beta. Which beta decay? Negative or positive? Huh? Which beta decay? Negative or positive? Positive positron emerge out, and with this positron, another particle comes out. What that particle is? What is the name of that particle? Neutri, neutrino. That comes out, and energy comes out. Okay. Now this hydrogen will combine through one more proton. First of all, this neutrino, which is being formed over here, this positron, it will combine with electron, and this process is called matter annihilation, in which two gamma rays emerge out. Okay, why two? Because to maintain the momentum. Okay. So if the one is move out, you have seen that in supernova or in those kind of stars, gamma bursts in both the directions like this. It is happening in both the directions. Okay, to maintain the momentum there. Okay, so two gamma particles has merged out. Another step, in another step, what will happen here? This nuclei of hydrogen again combine with proton and forms what it will form? H3, an isotope of an isotope of helium. Okay, it will form an isotope of helium. So here it was having one proton, one neutron. Here it is having one proton. Combined together, it is having two proton and one neutron. Okay. Now these two particles, again, these two isotopes of helium combined together and form a helium atom and again two hydrogen proton or two nucleus of hydrogen. Okay, so this is the combined reaction that takes place in steps, in different steps. Okay, so here it was having two protons and one neutron. Here it is also having two proton, one neutron, and in combined together it is having two proton, two neutron, and two proton. It is being balanced. You can see that it is balanced. It is gamma rays. Matter annihilation. Okay. Have you got that, dear? So here in each process, the energy comes out. Here the energy comes out about 0.4 mega electron volt, 0.42 mega electron volt. Here is also the energy comes out 1.2 mega electron volt. Here energy comes out. Here one gamma also comes out, and energy comes out to be 5.49 mega electron volt. And here the energy comes out 12.86. 12.86 mega electron. So when you combine all these reaction and write one reaction which is being written there in the your textbook, that is comes out to be one combined reaction, and that is basically 4 hydrogen nuclei combined together plus 2 electron and giving you helium nuclei plus 2 neutrino plus 6 gamma plus 26.7 mega electron. Okay, all of you can see that reaction now. Multiplying this by 2, multiplying this by 2, and adding all three. This will give you the end result. Okay. All of you can see the downward reaction.
That's a bit unfair.
Okay, now. Okay. So if you see in this whole process, the energy is coming out to be 26.7 mega electron volt. Okay. But this energy is very less as compared to the that we have seen in the nuclear fission reaction. In nuclear fission, energy was 200 mega electron volt that we have seen, but it is very less, huh? Isn't it? Here it is 26 point, but the difference is if you see the energy per unit mass, that is way more than the nuclear fission reaction and nuclear fusion reaction. Okay, if you see, so this 200 mega electron volt energy is being gained when you are using uranium U-235. Okay, then you are getting this much of energy. So energy per AMU is being given. We divide it by 235, which will come out to be 0.85 mega electron volt. Okay, have you got that? But here, what we have used, 4 hydrogen atom, and 4 hydrogen atom is being giving you 26.7 mega electron volt. Then energy given by per AMU will be how much? 26.7 divided by 4, which will come out to be how much? 6 point something, isn't it? 6.25 mega electron volt. So energy per unit mass is way far more than the nuclear fission reaction in nuclear fusion reaction. Have you got that? Have you got this point? Okay. Can I rub this now? Yeah. Some of the part of the semiconductor we have covered during the practical PN junction. Okay. Intrinsic, all that we have did. Okay, mostly. Some of the part is being remaining that we just complete. So, nuclear fusion reaction, we have seen this part. Okay. So, uh, hmm. So we have seen that the temperature is required at the power of 10 to the power 9 Kelvin, but sun is having a temperature of 10 to the power 7 Kelvin. So at this temperature, how the reaction is being taking place at the sun? When it is having temperature by 100 times less than the temperature required, because that is the average temperature. So this means some of the particles may have a temperature more than that. If they are having a temperature more than that, this means they may fuse together and carry forward the reaction, and due to which there are a lot of energy released, and which may increase the further temperature. Have you got that? Which may increase the temperature further. So we have seen that nuclear fusion is being used for destructive purpose like hydrogen bomb. But to trigger the hydrogen bomb, we also need the temperature of around 10 to the power 7 or 10 to the power 9 Kelvin. How do we get that temperature? So to huh? By heating, by fission. So we first trigger the atom bomb to trigger the hydrogen bomb. Okay, so here hydrogen bomb is not individually used. It is used with the atom bomb because atom bomb creates or release energy which increase the temperature by the range of 10 to the power 7 or 10 to the power 9 Kelvin, which trigger this reaction. And after triggering of this reaction, a tremendous of an amount of energy released, and which maintain its temperature by its own. Then after that, it do not require any further triggering or further atomic bombs to trigger that temperature. Okay, because if that nuclear fusion reaction starts, it may carry forward by its own, because it is continuously releasing the energy, tremendous amount of energy to increase the temperature by the range of 10 to the power 7 or 10 to the power 9 Kelvin. Have you got that? Hydrogen bomb, there is a lot of explosions are occurring there. Like it looks stable. So many solar storm continuously hits Earth. We have listened that this so many times news comes that the internet may not work, or that sometimes solar storm are so strong. So you see that what the distance is from the sun to the Earth, that is one astronomical unit. Okay, and by that distance, the energy is being carrying forward. So think that how much the hydrogen bombs has been fused there. Okay, have you got that, dear? So nuclear fusion reactions are in two cycles. One is proton-proton cycle that we have seen. Proton cycle. And one is carbon nitrogen cycle. So the reaction that we have seen over here, that is proton-proton cycle. Carbon nitrogen cycle happens in stars which are being having temperature more than 10 to the power 7 Kelvin. Okay, or 10 to the power 9 Kelvin of which they are having. There the carbon nitrogen cycle take place. What happened? The helium again start fusing together and form heavy nuclei, and this continue together and form carbon and nitrogen there. Okay.
Yes, sir.
In nuclear reactions, here we were getting by proton-proton cycle, we were getting the helium as a product. Okay. Here we will get the carbon nitrogen, but it will happen having a temperature may far more than the temperature of our sun. Okay. It happens. Okay, dear. Now this has been over, and semiconductor. So many things we have seen. Tomorrow we will complete the semiconductor, the things which are remaining. Or if you want, we can continue with the starting from the start. What do you want, dear? Yeah. So if you want, we can continue with the beginning, or we can con- continue with the rest of the part. Tell me. Okay. So uh, we have seen most of the things regarding that. Uh, uh, Only the application part is being remaining. Okay. That the where we are using the semiconductors. So many so many things in the semiconductor has been decreased. Uh, has been Okay, we will see the semiconductor part by tomorrow, same time. Okay. Yeah. Okay, dear.
Okay, sir.
Okay,
Thank you, sir.
start. Islam. Allah Hafiz.